Students, to this third lecture, and in this part we are going to talk about the Sturm-Liouville theory. Okay, so if you recall, the first two lectures was about Fourier series, right? Fourier series, and this part is also of a similar sort of thing, which is called Sturm-Liouville theory. And essentially what we are going to do is we are going to study a family of ODE in this part, and based on that we are going to deduce this Fourier series as a special cases. And then in the later part of the course, we are going to show you where exactly are we using this Fourier series and the Sturm-Liouville theory. So these two are very important topics basically to study PD, right? So first of all, let's start with our problem. The problem which we are interested today is this. See, first of all, we start with this. Let's start with the lambda, and for now we are just assuming lambda is a complex number, yes, and we will call this as a parameter. Yeah, this is our parameter. So this will definitely not depends on any variable x. So essentially for a given lambda, okay, so let's say we start with a lambda in C and we consider this particular ODE. Okay, consider the ODE, which is what is the ODE. So it will be given like this: a1 of x, okay, y double prime of x, okay, right, plus a2 of x, y prime of x, plus a3 of x, and this is where we are introducing lambda, plus lambda times y equals to 0. Clear? So this is just a type of problem which you want to study, and for now let's just call this as 1. Yeah, so for a lambda in C we are going to study this where you see ai's, okay, ai's of x, these are, for now let's just assume they are continuous functions. So essentially if they are continuous function, all of this is well defined actually, yeah? Function, yeah, and you can assume more. So basically without loss of generality, let us just assume they are smooth functions. Smooth means you can do as many differentiations as you want. Yes, let's just stick with that. So continuous functions where in some interval I is AB. Yeah, for now we are fixing some interval AB, which is which we are going to call I. See, in real problems we are generally AB will look like 0, 1, or let's say 0, pi, minus pi, this sort of thing. Yes, it depends, but basically we are working with a closed and bounded set I. Okay, so we have smooth functions in this interval I. These are AIs, and you see this notation which I am using, y double prime y a prime. I think you know this notation. Yn of x is basically the nth derivative. Yeah, this is what we mean, nth derivative of y, of the function y. Okay, so essentially y double prime is the second derivative, y prime is the first derivative. Yes, and this is the special type of ODE which we are going to talk about. Yes, now you see we know from our ODE theory, so this we should, I am hoping you guys already know, but if you don't know, let me just give you some ideas and you can check the so please check this part. I will definitely not do the whole calculation because I am supposing that you already know this from your ODE theory. Okay, so you check this, that if you, let's say, if you define P of x, okay, as exponential of integral a2 by a1, okay, and so basically P of x is, this is with respect to x actually, yeah, so the integral is on x, okay, and then Q of x if you define to be a3 by a1, okay, times P of x, of course, yeah, and of course a3 a1 I am just writing it like this, but a1 a2 a3 these are all functions of x. Yes, and if you define s of x, yes, this is just new sort of functions which you are defining here. So P of x, Q of x, and s of x. S of x is essentially P of x by a1 of x. Yeah, if we define something like this, yeah, then you can show, so check that if P, Q, and S are given like this, then 1 can be transformed as, can be written as, okay, written as, how can we write it? We can write it like this: P y prime whole prime plus q plus lambda s times y equals to 0. We can write it like this. Yeah. So this part you have to check. Please check it yourself. Okay. It's very easy to check. Essentially, I mean, this is the set of some sort of concept as integrating factors. Yes. So please do that. Right. Now the thing is, you do realize for this thing to work, you see a1 has to be non-zero. So in our assumptions also, so let's just add a little assumption here that a1 is non-zero. Okay, non-zero for all x in AP. We'll just assume this thing, yeah, because if it is 0, then basically the second order term is gone for that sort of x. So essentially we assume that this is not 0 for any x in AP. Yes, so all of this is very well defined, and we can write it like this. Yes, okay. So I hope you can check this part. Yes, of course, if you can't do that, you can consult any book how to do it. So this is basically the self-adjoint part. This is what we call this self-adjoint part. Huh? Let me write it this way. It's called the self-adjoint. Huh? Okay. Okay. Now, and you can, I mean, it's not a very difficult thing to do. I mean, check this. Yes. Okay. So, I mean, if you want a hint, you can look at this expression and try to put this sort of P and Q and S and try to write it in this. So, basically, you can go backwards. You can do that also. Yeah. Okay. Now, once that is done, so basically, 1 can be transformed into this part, 2. Yeah. And from 2, what we do is we write this new sort of operator. So, we define from 2, huh? We define the Sturm-Liouville operator. Yeah, Sturm-Liouville operator. Liouville operator. This is, please remember, operator means a function. Yes, and what do we mean by this? We will call it like L. Okay, and what is this operator? It basically, we'll write it like this. See, I mean, of course, we are putting dash here. Yeah, you can do that, but since that requires a function, so we'll write it like this: d x of p d dx. Okay, this one plus q. Yeah, so essentially you do realize, so essentially what happens is this, I mean, if I am putting it into context, let's say L of a function u, a nice function u, that will be basically d dx, okay, of p d dx of u, okay, plus q times u. This is how we define it. Yes, and then this particular thing, if you look at it, we can write it like this: p u prime whole prime plus q u, right? Because du dx is essentially u prime, right? So we can just write it like this. So this is how. So I mean, we write this operator. So how are you getting the idea? You see, this particular term, this first term, p y prime whole prime, this is your term. This is the term. Huh? So instead of u, you can write it as u. And this qu, so essentially qu here is, you see, with respect to this u, the coefficient of u is some function. Yes, so you see the coefficient of u is y here, so it's basically some function. Of course, here it depends on y, but generally speaking, for a Sturm-Liouville problem, we just write it like this. Okay, so we will define this operator essentially. Yeah, we define this operator, and this operator is like this. What is it? This is p. So if you want, you can think of it like this. You see, if you are confused here, you can please write it as y also. Huh? Doesn't matter, same thing. P this. So essentially, what is the operator? If you want to write it, it is p y prime whole prime plus qy. So that's your Sturm-Liouville operator, if you remember it. Huh? Okay, right. So see, again, let me emphasize a little bit. What do I mean by a operator? Okay. See, here L is a function. You see, this particular object, what is this object? This object, we are calling it as an operator. Okay, and what does it mean? It means that if you fed, you see, function is what? Function is you feed something from the domain of it. You take something from the domain, you feed it to the function f, and that will give you some output which will be in your set, the range, right? Okay, so these operators also functions, yes, but these functions, they actually a special kind of functions. And what do you have to feed those sort of functions? So the operator L, it feeds on functions itself. Okay, so basically let's say y is a function, and what sort of function can y be? See, y has to be at least twice differentiable. If y is twice differentiable, d dx of y makes sense, and then that will be once differentiable. And let's say p is smooth, so the whole thing is smooth, and then you can talk about the derivative of that smooth map. Okay, let me again recall what I am trying to say here. See, let's say y is twice differentiable function, right? Twice differentiable, c2 means twice differentiable function. Okay, so if y is c2, it means y prime, which is this particular d dx of y prime is c1, yeah, and p is smooth. So for now we can assume p is c infinity, smooth, right? Infinitely differentiable. Okay, so you see p times y1, p times y prime, so that will be c1. This is c infinity means p is c infinity means p is c1. It's a c1 function, y prime is c1, so the multiplication of two c1 function is going to be c1. Now if it is c1 function, it is once differentiable, right? So we can talk about the derivative of this particular function, and this will be a continuous function, right? And then also you have q is infinity, c infinity function, very smooth, and y is c2, so y is also continuous. So basically this q times y is also continuous, so qy is also continuous function, yeah, on whatever interval, let's say in this case I. So you do realize that if you are taking y from c2, the resulting L of y will be a continuous function at least, right? Okay, so let's put it this way. And if you can also check that for now, let me put it this way. Y is called operator, so essentially where does L work? So please check that if you can think of it like this, L from c infinity to c infinity I to c infinity I. C infinity I, what is c infinity I? C infinity I is the set of all infinitely differentiable functions on I. Okay, c infinity I is the set of smooth functions. Okay, so set of infinitely differentiable functions. It means you can take derivative as many times as you want. Infinitely differentiable functions on I, functions in I. Okay, so this is c infinity. So this infinitely differentiable part we are trying to call it as a smooth function, smooth class of function. So L is from c infinity I to c infinity I. Again, what do I mean by this? I mean that if you feed a smooth function, so what are the examples of smooth function? Let's say exponential, sines, this sort of functions. If you feed L, so L of exponential, you do realize that all of this will make sense then, yeah. So that will give you back another function which is will be a c infinity function. That's the gist of it, provided q and y are smooth. Okay, so that's the idea. Essentially what I am saying is L is an operator in such a sense that if you give it a c infinity function, it will give you back a c infinity function. The output will be c infinity. Yeah. Okay, fine. So I think that is more or less clear why we are calling this as an operator. Okay, now you see, if you call L as this operator, then these two, if you think of it, you see p y prime whole prime plus q y plus lambda sy, this extra term is there, yeah. See this part, p y prime plus q y, this is your this part, right, plus lambda sy part is there. So we can write 2. So one can rewrite 2 as, okay, how can we write it? Let me put it this way. It is L of y plus lambda sy equals to 0, right? If you put it this way, so L of y plus lambda, see s depends on x times y equals to 0. If you want, you can just put it this, I mean in many books they actually write it like this, L of y. Okay, just to make it a little different. So basically you mean that L is an operator essentially, yes. Okay, so we write it like this. Now again, what is lambda here? Lambda is a parameter, of course, which is independent of x, as I told you. I told you somewhere, right? I forgot. Yeah, you see, it's some parameter, and of course it does not depends on x. Yeah, and what are these in L? you see L is this operator, right? L is P y prime whole prime plus Q y. Yeah, this is what. So here P and Q are smooth functions. Okay, smooth functions means they are C infinity functions. We are just assuming this. Yeah. So here assumptions, let me put it this way, assumptions, so that there is no confusion. Assumption P, Q are smooth functions. It means infinitely differentiable. Yeah. Sorry, and S is also. Yeah? And lambda is in C, is a parameter. This is called a parameter. We will call it a parameter. Okay, right. Now I will explain to you what all of this means. Yeah, right. Now the thing is this, you see, so essentially we will start with something called a Sturm-Liouville equation. So this is, you see, up till here it is a Sturm-Liouville operator we defined, and this is the original equation 1. We have multiplied using integrating factor and got this self-adjoint form, which is this. Yeah, this form we are writing it in terms of a Sturm-Liouville operator, which looks like this. I hope this is clear. Okay, now we are going to write down what is a Sturm-Liouville this thing. What is it? Sturm-Liouville equation. Yes. Okay. So you see, we'll call, so we'll define regular Sturm-Liouville, regular. So I don't want to write Sturm-Liouville all the time, so I will write it as SL, regular SL system as follows. So we'll define a new system. System means a equation with a some data. Yeah. So what is the data? You see, we start with this L of y plus lambda s of x times y equals to 0. Yes. And of course, what is x from? X is from I. And now we are defining it to be in AB. Yeah. So this is your equation part. Now we will have some conditions. What are the conditions? The conditions is this: A1 times y of A plus A2 times y prime of A is going to be 0. Okay, and B1 times y of B. See, this is called regular Sturm-Liouville problem. So basically this these two conditions, okay, let me write it down and then I will explain. B2 times y prime of B equals to 0. Is it okay? So here the assumption is A1 square plus A2 square is going to be non-zero, and similarly in the next one the assumption is B1 square plus B2 square is going to be non-zero. Okay, let's just understand. First of all, these two conditions, these are basically the regular Sturm-Liouville conditions. We will also call it a separated end condition. Separated end condition. Okay, and essentially see, you see this the first condition. Let us look at first condition. So basically the first condition gives you the information on what y and y prime does at the point A, and the second condition tells you what y and y prime does at the point B. Okay, so at the two endpoints, what y and y prime does, those are the two conditions which gives you. Now what about A1 square plus A2 square not equals to 0 and B1 square plus B2 square not equals to 0? See, if A1 square plus A2 square is equals to 0, it means that you do not have any condition. So if it is equals to 0, the first condition becomes invalid. And similarly, if B1 and B2 are both 0, then the second condition is invalid. So basically what I am saying is this: with these two conditions, both, I mean, we have to have information both at the point A and at the point B. So basically we should have information on y or y prime or both at A and B. So at both the points we should have information either on y or y prime or on both. Is it okay? So that is why this sort of problem, these are called boundary value problems. So basically this is a special sort of equation. These are called boundary value problem. Is it okay? So this sort of problem is called a boundary value problem. Boundary value problem. Okay. So initially I am going to start with something called, so this sort of equation which is called a regular Sturm-Liouville system. What is the system? You have this equation where lambda is a parameter given like this, and then these two boundary conditions are there, at the point A and at the point B. Two conditions are there, and we'll call it a regular Sturm-Liouville boundary value problem essentially, but you can also call it as a regular Sturm-Liouville system. Is it okay? So first of all, what we do is, see, we want to find out a solution of this equation. Okay, solution of this equation. Now let us understand one thing. See, solution for what? What is the question we need to first of all answer here? So this sort of question here, if you think about it, see, this kind of question is called an eigenvalue problem. If you remember your matrix thing, yeah, so we talked about this thing, right? In the, so in linear algebra, you know, this sort of thing happens. So basically you are given a matrix, let's say n cross n matrix, and then a equation will be like this: ax equals to lambda x. Now the question is this: you have to find lambda for now, let's just say in C, you have to find lambda in C such that you have to find such lambdas for which there are non-zero x, right? X not equals to 0. The vector x should be not equals to 0. Basically, you have to find lambdas which actually admits non-zero x such that x equals to lambda x. Yes. Okay. Why non-zero x? Because you see, if x equals to 0, so basically for any lambda x equals to 0 is a solution. And similarly, this is also a same sort of problem. You see, Ly plus lambda Sxy equals to 0, right? So you see, it doesn't really matter what. So now, if I want to talk about this problem, let's say, yeah, let's come back to the ODE part. See, if y equals to 0, yeah, why this is not a valid thing? Because y equals to 0 works for any lambda. You see, it does not really matter what lambda is, y equals to 0 always works. Okay, so you understand that y equals to 0 is not going to cut it, right? So what we want to do is, the question is this: question is find lambda in C such that, let's call this problem as 1, 3, okay, such that 3 admits a non-trivial solution. Okay, so what does that mean? Non-trivial solution means essentially when I say y equals to 0, it means, see, this is always a solution, is a solution. So this is a small note, note. Y equals to 0 is always a solution for any lambda, right? So essentially we are not interested in that, yeah. And when I say y equals to 0, what do I mean? I mean yx is equals to 0 for all x in I. This is what I mean. Okay, so you see, what we want is, we want a solution y which is not 0 at least at one point. By neighborhood property, if it is non-zero at one point, it has to be non-zero at least in some open neighborhood, right? So basically we want a non-zero solution in a non-zero solution, and we want to find lambdas such that that thing happens. Yeah, if we can find such lambdas, okay, so if such lambda exists, we call them eigenvalues of the system values, and the solution y, okay, depending on, of course, lambda, depending on that particular lambda, whatever lambda. So the non-zero solution which you are going to get, so of course that is non-zero, okay, not equals to 0, essentially y lambda corresponding to this lambda, the y lambda which you are going to get is called the eigen function. Okay, function. See, in the earlier case, in matrix cases, we need to call eigenvalue and eigen vector, right? Here we will call it as a function because this is a function, you see, y lambda. Okay, right. Now, before, enough of theory and all, let's just work out one problem so it becomes very clear what we are trying to do, and then we will look at more theory. Okay, so let's look at one problem. So example 1, yeah. So I think this will be very crucial example for you to understand what's going on here. So this is the problem we want to talk about. Y double prime plus lambda y equals to 0. First of all, let's just check if it is in this form or not. See, if you put P, Q and S to be 1, then we are in this form, you see. Yeah? So this is for the form, if you can check P, Q and S is 1. Okay. This is in AB. Okay, for now, well, let me just put it as 0 pi in 0 pi. So basically A is 0 and B is pi, and then you have this initial condition y0 equals to 0 and y prime of pi is equals to 0. See, if you check with this condition, you see here A1, A is 0, B is pi, A1 is 1, A2 is 0, B1 is 0, B1 is 1. B1 is 0 and B2 is 1, right? And then we will get this condition, you see. Please check this part, that if this is a regular Sturm-Liouville problem or not. But of course this is, which is quite evident. So let's just call this is as the fourth problem. Okay, we want to solve this problem. So essentially, what do I mean by solving this problem? We need to show whether there are some lambdas for which there is a non-zero solution. Of course, y equals to 0 is always the solution for any lambda, as you can check. Okay, now let's say when so first of all, for this problem to work, yeah, of course lambda is complex, yeah, but we will restrict ourselves to only real values for now. So we restrict lambda in R. Yeah, I will explain to you maybe in the next video why we are only restricting it to R. Essentially this is enough, yeah, but there is some theory behind it. We will talk about the theory and then it makes all sense. But for now you don't have to talk about any complex lambda, just stick with R. Okay, so first of all we'll do it this way. See, case 1. What is the case 1? Let's look at if lambda is negative, less than equal 0. What happens then? Let's just understand this here. If lambda is 0, then you see lambda can be written as minus mu square, right? And let's say mu is non-zero. Mu is non-zero, right? We can of course write it like this, yeah. Okay. Of course, lambda is real. You see, this is why this we can write it as the lambda equals to minus mu square, right? And why minus? The mu square is always positive for any non-zero mu. So minus mu square is negative. So lambda is less than. Okay, let me do it as less than 0, not less than equals to 0. Strictly less than 0, negative. Okay. Now, or maybe I can do it for less than equals to 0 together. Let's do it for less than equals to 0. So if lambda is 0, mu is also 0. Okay, lambda less than equals to 0 together. Let's do that. Okay, generally speaking, we'll do it in 3 cases: lambda negative, lambda equals to 0, and lambda positive. For now, for this first problem, let's just do it together. Okay, if this happens, then what is the problem now? We have this y double prime minus mu square y equals to 0. Yeah, this is the first problem. And you do realize if this is your problem, then you can of course check that what is yx. Yx in this case is some constant a1 times e power mu x plus b times e power minus mu x. I think I do not have to explain to you how this is coming. This is basic ODE theory and you can take care of this thing. So a, b are constants basically, are constants. Now the question is this: how do you find out what those constants are? How do you find out? We put the initial condition here. So let's just put it. See, first of all, the solution y0. So this is our general solution, right? Now you see the general solution y0 has to be 0. So basically 0 is y0, which is a times e power mu times 0, e power mu times 0 plus b times e power minus mu times 0. So essentially what are you getting from here? A plus b is going to be 0, right? And you also have this another condition, y prime of pi is 0. Okay, so 0 is y prime of pi. Let's just understand what y prime of pi is. You can check from here. Y prime of pi is a mu times e power plus mu x minus b times mu e power minus mu x, right? And x is pi here, so let's just put that pi over here and see what happens. See, there will be pi here and there will be pi here. Yeah. From this condition we are getting a equals to minus b. See, any solution of this equation looks like this. This is a general solution. So we are trying to find a solution which satisfies these two conditions. So if it satisfies these two conditions, A has to be equals to minus B, and this condition is also true. If this and this is also true, this actually imply that A times mu e to the power mu pi minus B is again A plus A times mu e to the power minus mu pi is going to be 0. So that will give you A times mu, common if you are taking, it is e to the power mu pi plus e to the power minus mu pi is going to be 0. Now this term of course is never going to be 0, that's for sure, right? It's an exponential term. So essentially that will imply A times mu has to be 0. Now can mu be 0? Of course mu can be 0. Yeah, see, mu can be 0. You see here, if lambda is 0, mu can be 0. Okay, so for now, first see, this is subcase. Okay, A, let's say, if mu, so basically if lambda is strictly negative, so in this case mu is definitely not 0. If mu is definitely not 0, A has to be 0. Clear? Now if A has to be 0, A is equals to minus B, that will imply B has to be 0. Now if A and B is 0, you see yx is what? That will imply yx has to be 0. See, yx is A e to the power ux plus B e to the power minus mu x. If A and B are both 0, yx has to be 0 for all x. Is it okay? So in this case yx is 0, and 0 is not a solution which you are looking for, right? Because that can't be an eigenfunction. So lambda negative is not going to work. Okay, right. So let's look at this. Subcase B. Okay, what happens if lambda equals to 0? If lambda equals to 0, of course mu is 0. Okay, see, lambda equals to 0 is mu is 0. If lambda equals to 0, I am putting if basically I have y double prime equals to 0. So that will imply, hence that will imply y double prime equals to 0. Yeah, and this will imply that y equals to ax plus b. Okay, I think it is better to do it this way. So first of all, let me rephrase this problem a little bit. Let me do it for this lambda negative as case 1. Let me do it this way so that you may not get confused. Let's just change it this way. So you see, let's now do it as a subcase. Do it like this. Since y lambda negative, yx equals to 0, hence we can conclude that lambda negative is not an eigenvalue. It's not an eigenvalue. I hope this is clear. Okay, I'm just changing it a little bit. I don't want to do it together. We can of course do it, but I mean it is better not to in this case. Okay, let's just understand what happens when. So let me put it this way, case 2. What is it? Lambda equals to 0. So if lambda equals to 0, you see the equation becomes y double prime equals to 0. So that will have y double prime equals to 0, and the general solution will look like this: yx equals to ax plus b. You can check this. I am not doing this thing. This is very easy to do. A and B are constants, are arbitrary constants essentially. Arbitrary, real constants, of course, constants. Okay. Now you see our initial condition: y0 equals to 0. And so that will give me A times 0 plus B. So this implies B equals to 0. See, I am putting x equals to 0 here. So if I am putting x equals to 0, A times 0 is 0 plus B, that is going to be 0. So B is 0. And you see 0 is y prime of pi. This is another condition. So 0 equals to y prime of pi. What is y prime of pi? This is basically A. So that will imply A is going to be 0. So from this you do realize that A and B is 0, hence y has to be 0. So that will imply y equals to 0 is the only solution. Okay, but we are not looking for the trivial solution. Hence lambda equals to 0 is also not an eigenvalue. Okay, now the question is this. So see, lambda negative is not an eigenvalue. Lambda equals to 0 is not an eigenvalue. So what is an eigenvalue? Okay, so let's do this. So case 3. Are there any eigenvalues? Case 3. Lambda positive. This is our only hope, right? So if lambda is positive, then I can write lambda equals to mu square, right? Of course, mu is not 0. Okay, I can write it like this. Now, once I write it like this, the equation becomes y double prime plus mu square y equals to 0. Yeah, and that will guarantee us that yx will look like this. If you know how to calculate this thing, it is a cosine mu x plus b sine mu x. Okay, right, and again a and b are arbitrary constants. I'm not writing the whole thing down, but you do realize the same thing, constants. Okay, now our initial condition. What is our initial condition? The first condition is this: y0 equals to 0. So let's put it this way: a times cosine mu 0, cosine mu times 0, plus b times sine mu times 0. Okay, see, sine 0 is going to be 0, and cosine mu times 0, so cosine 0. A cosine 0 is 1, so this will imply a equals to 0, right? A equals to 0, because b times 0 is going to be 0, so basically we are left out with a equals to 0. Okay, now let's just hope b is not 0. Okay, and you do realize that 0 equals to y prime of pi, right? Now, what is y prime of pi? See, if you're taking the derivative here, it is becoming minus a pi times sine mu pi, right, plus b mu times cosine mu pi. See, this is what we are getting it. But the thing is, again, a is 0. Yeah? So this particular term is gone. So essentially that will imply that b mu times cosine mu pi has to be 0. Yeah. Now, what does this imply? See, there are two cases here. Can mu be 0? See, mu can be 0. You see, mu is not 0. So mu is not 0. So since mu is not 0, this is out of the question. So basically it means b times cosine mu pi is 0. Okay, but so this will imply, let's just see, there are two cases here. B is 0. If b is 0, then what happens? Y has to be equivalent to 0, because a is 0, and if b is 0, then you see this y becomes 0. Not interesting. So not an eigenvalue in this case, not an eigenvalue. So not interesting. We will not involve with that. So our only case is when cosine mu pi is going to be 0. Yeah, let's just understand this thing. Okay, see, if cosine mu pi is 0, so basically b is not 0. Yeah, b is not 0. Here b is not 0, but cosine mu pi is 0. Yeah. Okay, if cosine mu pi is 0, we need to know when is cosine 0, right? Cosine is 0 if mu pi is nothing but 2n minus 1 by 2 times pi, right? If you remember, yeah? When is cosine 0? Essentially, these are the pi multiples where this is 0, right? So basically this is for n equals to 1, 2, 3. These are the multiples where of pi where cosine is 0, right? So this will imply that mu is basically 2n minus 1 by 2. Yeah, and n is in n essentially. Yeah, so you see, what is mu? Mu is root pi lambda. You see, yeah? Mu is root lambda. So that will imply that root lambda is this. Yeah, so one second. Let me. This is lambda is 2n minus 1 by 2 square. I hope this is correct. Let me just check. Your lambda is mu square. So lambda is mu square. Yeah, this is okay, right? So this is the thing. So basically this is 2n minus 1 square by 4, and n is in n. Okay, that's your lambda. Okay, so see, for these lambdas, there are non-zero solutions. Clear? Yeah. So this lambda, of course, they depend on n. See, this is not a single lambda, but there is like a sequence of lambda: lambda 1, lambda 2, lambda 3, lambda n. Yes, and lambda, it goes on, right? And moreover, you see, there are some corresponding solutions. What are the solutions? Moreover, what are yn of x in this case, and yn of x is basically it depends on lambda, right? So they are in this case, see, essentially if lambda n's are 2n minus 1 by 4 essentially, yes. See, in our case this is the case, right? So a becomes essentially 0. So the solutions are b times an arbitrary constant times sine mu x. So essentially this is some constant up to a constant. Let me put it this way. This is equals to sine of 2n minus 1 times 2 times x, yeah, up to an arbitrary constant. Is it okay? Up to an arbitrary constant, yeah, we can write it like this. So essentially you see the eigenvalues, the eigenfunctions, so eigenvalues are this and the eigenfunctions are the sine functions, yeah. Of course these are for n in n, for n in n, yeah. Now why are we not putting an arbitrary eigenfunction? Because you see this equation, if you look at this equation, the earlier equation, you see this equation, the original equation, this is the equation, right? Yeah. So you see, note, let me put it as a small remark. There are two conditions of this. This is a linear equation, right? So if y is a solution, then a constant alpha times y is also a solution. You can check it easily, right? It's a linear equation, also a solution. It's a linear ODE, so this is true, right? Okay, so if this is true, then you see basically if this is a solution, sine of 2n minus 1 by 2 times x, then any constant multiple is also going to be a solution. So there is no, so I am just taking this thing to be our eigen function. Is it okay? So basically what are the eigenvalues? Lambda n, and the eigenfunctions are given by yn. These two put together are called eigenpairs. Is it okay? And how is it given by? They are given by this 2n minus 1 square by 4 and comma sine of 2n minus 1 by 2 times x. Is it okay? So this is the eigenpair for this particular thing. Of course n is in n. Okay, now once the problem is done, let me just explain to you what all of this means. See, what all of this means is the equation, if we, this is our original equation, right? Y double prime plus lambda y equals to 0, right? Now in this equation, if you are putting lambda to be 0, there are no solutions. Given this in boundary condition, lambda equals to 0, no solution. Lambda negative, no solution. Okay, what about lambda positive? Lambda positive only if lambdas looks like this, 2n minus 1 square by 4, then you have non-trivial solutions. Is it okay? That's what this means. Lambda equals to 0, no solution. Lambda negative, no solution. And for lambda equals to 2n minus 1 square by 4, they have solutions, and the solutions are given like this. You see, sine of 2n minus 1 by 2 times x. I hope this is clear, and this is called eigenpairs. So this is how you solve the problems. Okay, so with this we are going to end this video. In the next video we are going to talk about more problems. There is another condition which is called periodic boundary condition. We are going to talk about it, and we are going to look at more problems.